In example 2, we are going to try to come up with some patterns that we can see when we are working with modular arithmetic. So let A be the set of all integers, little a, such that little a mod 5 is equal to 2, and B is a set of all integers, B, such that little b mod 5 is equal to 4. Before you watch the rest of this video, see if you can write down the list of elements of the sets A and B. So just pause and write down what numbers will be in A, what numbers will be in B. Okay, I hope you made your own list. See if we agree. Oops, I don't want that color, I want blue. So let's see what we can find for A. What are all some things that are in A? I want everything that is equal to 2 mod 5. So has a remainder of 2 after I divide by 5. One thing that's definitely in there is 2. I'm going to put that in the middle because there might be some smaller and some bigger. Oops. What else? The next one would be 7. And then the next bigger one would be 12. They all have a remainder of 2 when divided by 5. And so on. You kind of get the picture. Negative numbers can be in here too. So what negative number has a remainder of 2 when divided by 5? The first one would be minus 3, and then before that would be minus 8, and so on. So here we have a systematic enumeration of everything that's in set A. In set, and you can see what patterns you all notice when you're looking at that. For B, we are looking at everything that is equal to 4 mod 5, so 4 is definitely in here. And then what's the next bigger one? That would be 9. So if I take 9 and divide by 5, it's 5 plus 4. So yep, 9 is in there. And then the next one would be 14, and you can convince yourself and see what else. But we're basically just adding 5. That will give us the next number that has the same remainder of 4. And we can also go in the other direction, and we get minus 1, and then we have minus 6, and I hope you see the pattern right there. In part B, we want to just look at several choices of elements in set A and B and calculate A plus B mod 5 and A times B mod 5. So we could just pick a random number out of A, let's say 2, and then pick a random number out of B, let's pick 4, not so random, but I'll start with that. And let's see what we get, mod 5. So 2 plus 4, that is 6, mod 5, that's 1. Okay. Let's pick some other numbers. How about 7 plus 4? So again, something from set A, something from set B, mod 5. 7 plus 4, that's 11. I divide by 5. That gives me a remainder of 1 again. Let's pick some other ones. How about 12 plus 9? I could really pick any two. Pick some other ones if you like. 9 plus 12, that is 21. I divide by 5. I get a remainder of 1 again. So it looks like all of these will give me a remainder of 1. Well, we only have 3 examples, that's no proof, but anyway. Let's look at the product of the same two numbers. So 2 times 4, mod 5. 2 times 4, that's 8, mod 5 is 3, remainder of 3. What about 7 times 4, mod 5? 7 times 4 is 28. 28 divided by 5, that is 25 plus 3. Up, it's 3 again. And 12 times 9, you can do the arithmetic. If we're going mod 5, that is also 3. You can convince yourself that that is true. And for any other product of numbers, one from set A and from set B, we would have gotten the same thing. So the answers are the same. In each column. Coincidence? Probably not. And in fact, if you go to the next page, theorem 0.b over here summarizes that this result holds in general. So if we have two numbers that are the same mod n, so in our case I have a and I have a prime, and they are the same remainder after division by n, and the same is true for two other numbers, so b and b prime also have the same remainder after division by n, then the product of those two numbers will be the same. Or actually the product of a and b will be the same as the product of a prime b prime, which will be the same as just multiplying those remainders together, mod n. And the same is true for the addition as well. So for the sum of a and b, a prime and b prime, and r1 and r2. So that is one theorem. The proof is in the notes. So take a look at them, or even better, try to see if you can prove it on your own, and then look at the notes to see how close you are in your proof. There's one other very useful fact that we're going to be using a lot, and that is theorem 0.a. If we have integers a, b, and n with n greater than 0, then two numbers are equal mod a and n if and only if n divides the difference. So that goes into the blank, n divides a minus b. That is going to be a very useful fact that we're going to use a lot when we want to we need an operation that tells us when two numbers are equal to each other, mod n. So keep that in mind. You will see that a lot, and you will also be using it a lot in the future.